Hello, everybody. Welcome to today's Combustion webinar and happy Friday. So today it's my great honor to introduce you or invited speaker, Professor Michael Zachariah. Professor Michael Zachariah is Distinguished Professor of Chemical Engineering and Material Science at the University of California Riverside. He has extensive experience in the synthesis of nanomaterials and characterization of their reactive properties. And he has worked extensively on aerosol-generated materials and the metrology of nanoparticles in both the liquid and gas phases. And this includes the development of new mass spectrometry and ion mobility methods to characterize nanoparticles and their reactivity. Professor Michael Zachariah's primary research focus now is directed towards exploring the thermochemistry and kinetics of energy-dense materials and methods for their temporal and spatial reactivity. Professor Zachriah is a recipient of the University of Maryland Outstanding Researcher Award and the Sinclair Award for Sustained Excellence in Aerosol Research awarded by the American Association of Aerosol Research. And with that, I would like to thank Professor Zachariah for being a speaker, and the podium is yours. Thank you.
Well, thank you very much. I appreciate the invitation, the opportunity to come and talk to you. And now I notice an old friend of mine is in the audience, Phil Westmoreland. I hadn't noticed that, and I saw his picture up there. Hello, Phil. So with that, I'll start. I'd like to tell you a little story. The presentation is a story of a mechanism of how nanoparticles might react in energetic systems. And so there are a number of students who have been involved because I'm taking bits and pieces of students' work and cobbling it together into a story. So basically the idea is when you have metals or metal oxides, a lot of what we do industrially is really move oxygen around. We do a lot of that for energy applications. Of course, when we burn hydrocarbon, it's not a metal, but we are moving oxygen around. And so we do this quite often. So an example of thinking about this, here I'm writing a thermochemical cycle of a model hydrocarbon in which we can react it with the metal oxide as the oxygen donor to make carbon dioxide, water, and the metal. Now, why would we want to do this is that we can then take the metal and then react it with air to recover the metal oxide. So thermodynamically, this is equivalent to reacting material with air. The advantage, of course, is that in the top cycle, you only have one gas stream, carbon dioxide. You don't have to separate carbon dioxide from nitrogen, which is a difficult thing to do. So there are other examples. We could take metal and react it with water to generate hydrogen and metal oxide. Of course, you need to recover this metal oxide, and you do that by boiling the oxygen out using solar light to recover the metal. And so essentially you're converting water into hydrogen this way. You can imagine that you could take carbon dioxide and also react it with water to make carbon monoxide, which is in its own right a good fuel. And then you do the same recovery process. So if you take water and CO2, you make hydrogen and CO, which of course for Fischer-Tropsch, you can make liquid hydrocarbons. And then you could go back up to the top here and do the same process all over again. So these three comprise a closed loop system if you could choose the right metal oxide and the right reactors. There are a lot of details that would have to be worked out, but basically the concept of moving oxygen around. And you know, you can imagine other examples in hypersonic combustion where where you could pre-mix fuel with metal oxides as an ignition source. And I'm going to spend a lot of time on this example, metal plus a metal oxide, where you get the exchange reaction. This is a famous thermite reaction. And we're going to spend some time talking about this because the energy density of this is quite high. So this is the example now of water reacting with aluminum particles. And I have a hot wire here. And on the wire, I put nanoparticles of aluminum. And in the background is water vapor. And what you're seeing is the light emitted from the combustion of these nanoparticles of aluminum. So they're glowing because they're hot, because they're reacting with the water. So you can think of this as a hydrogen production source in the way that I just described. And by the way, that movie was fast. It was a 4-millisecond movie. So you saw less than a millisecond of it. Of course, we're familiar with, Space Shuttle rocket booster, which uses aluminum as a fuel and an oxidizer. There are other ways. You could do the aluminum water reaction I just showed you, but you can do it to do pressure volume work. So this is an example of work by NASA and Steve Sun, in which this rocket is really powered by ice and aluminum to make aluminum oxide and hydrogen. And the hydrogen is just doing basically work. And you can see the hydrogen burning in the afterburner here. So you can use it as a production tool. You can use it as to do work. So these reactions, as I said, are very high energy density. Just to do a comparison, here's thermodynamics of metal oxide. These are aluminum plus molybdenum oxide, or aluminum plus potassium perchlorate. And then I'm comparing that with what we consider high energy dense materials, explosives. And you'll see that the energy density of these metal oxide systems is usually about a factor of 2, depending on the metric, relative to the higher explosive. So in terms of energy density, these kinds of materials are the best you can do right now. However, the kinetics are slower. Why? If you think of a traditional explosive material here, the red comprises, if you like, there's probably not too many chemists here, so I probably won't be too heavily criticized. The red part probably comprises the fuel, and the green part, the oxidizer. And you can see the fuel and the oxidizer are separated by only a few angstroms. So in terms of diffusion lengths, there's not far to go to mix the fuel and the oxidizer. And so things happen very, very quickly. On the other hand, if I take aluminum and copper oxide and mix it, I have an amalgam of an irregular shaped thing, and the diffusion lengths are going to be completely different and much, much longer. The fuel has an oxide layer that's going to be a barrier to transport. And we've got two solids here, and in order for two solids to react, something's got to move. So what's moving here we'll talk about that in a minute. So the motivation for understanding that, first of all, is going to be, thermodynamics. We know the energy release is more than carbon, hydrogen, nitrogen systems, but the kinetics are going to be slower, which is why people have gone to nanomaterials, because diffusion lengths effectively are shorter. And so you go to a nanomaterial to do that. And despite that, they are going to be much, much slower than molecular systems. But we really don't understand these mechanisms. So if I just ask from an energetic standpoint, is there more energy in a nanoparticle? So what's the smallest nanoparticle I can make? Well, it's really not a nanoparticle, but let's first do standard thermodynamics. If I look up in the Janif tables, aluminum bulk plus oxygen gives you this much energy. This is delta H of reaction. And again, if I wanted to do a nanomaterial, what's the smallest entity I could imagine? Well, actually, it's a single aluminum atom. And if I look up that thermo, I get this number. And the ratio of these two is 39, 1.39 rather. In other words, the difference between these two is only 39%. And by the time I get to a 1 nanometer particle, I only have 4% more energy. In other words, if one considers the surface energy of a nanomaterial, it's not really going to be that important. I can only get a few more percent out of this, and that's just for something that's a nanometer. So really, it isn't going to be about energy. This is all going to be about kinetics and how fast things can happen. So if one wants to design a fuel oxidizer system, we really need to understand how they react. So questions like, I know oxygen's got to move. Does the oxygen come out of the copper oxide and then somehow get into the aluminum in the gas phase? Or is it concerted condensed phase reaction? That would be a useful thing to know. And so how are we going to think about that? So first we have to ask how we're going to characterize this. We're going to do it by a few different ways. One approach is to do rapid heating on a wire. You coat your material on a wire, you heat this wire by Joule heating, and then things were going to come off the wire, which you can detect, or light will be emitted, which you can detect. And so this is what an image looks like from an event on this wire. And we can do color pyrometry, which I'll discuss later, to get the temperature profile. And the wire itself can act as a thermometer. So this is the wire being ramped in time. And the light emission is basically when ignition occurs. And this gives us the ignition temperature. So you can use the wire as a thermometer to get ignition temperature. You can look spectroscopically what's going on as well. And if one were to do X-ray imaging, this is what happens on the wire as I heat the wire. This is total time of 1.8 milliseconds. You can see the material coming off the wire and reacting and combusting. Just show that one more time. This is an X-ray image, but you can see what's going on in the system. Now, if we bed this into a mass spectrometer, what you can do is you can heat the wire, material comes off the wire. You can then ionize that with electrons and then do time of flight mass spectrometry to enable you to get a mass spectrum at a high rate. So we can pulse this process at around 20,000 hertz so that you can get multiple spectra. So this is what spectra would look like. This is time in milliseconds. This is mass over Z. And this is the red points to temperature. And so you can see various species come along and be formed and then disappear. And you can dig into what those species are and try to extract information about the trajectory of these condensed phase processes that are going on. So let's think about the oxidizer. So here is copper oxide. I've just taken copper oxide. There's no fuel here. And I'm going to heat that up on the wire. This is a 70 micron wire. And you can see these are nanoparticles. And you can see this bubbling going on. That bubbling is because oxygen is being released. It's an oxidizer for our purposes. So if you heat it up, you're going to get oxygen coming out. And of course, since oxygen is coming out, we can put it in our mass spectrometer. And as a function of time, you'll see peaks for oxygen. And these are different oxygen peaks for different oxidizers. So different oxidizers are going to generate oxygen at different temperatures and at different rates. And that should, in principle, have a big impact on how it reacts with a fuel such as aluminum. And so, in fact, if you look at something like the pressurization rate, which is you put everything in a little closed container and you light it, you can see that the pressurization rate, which is pressure per unit time, can vary depending on the oxidizer. Iron oxide is very weak, silver iodide is very high, and that actually corresponds with the ordering of the oxygen release in our mass spectrometer. So these two things must be connected. And so here we can see oxygen. This is what the mass spectrometer profile looks like temporally from copper oxide as we move it in time. And interestingly, if I were to look temporally, you will see two peaks for oxygen coming out. One CuO going to Cu2O and another Cu2O going to copper. So we see both phase transitions, but this is a relatively low heating rate, only 3,000 Kelvin per second. If I went to 500,000 Kelvin per second, we only see one peak. And what's really happening here is that this is so aggressive that we don't really distinctly go through various phases. We're just ripping oxygen out of the system. So really are now kinetically controlled. We're not passing through the thermodynamic phases we normally think of in a reduction process. And that's sort of going to be an important concept. So we can extract, for example, the activation energy for oxygen release using these experiments. And these are examples of that. Those Arrhenius plots. I'll just summarize the data for you. So here is what happens when you do things at slow heating rates, 5 to 30 Kelvin per minute, where you're sort of passing through thermodynamic phases. This is the kind of activation energies one measures. But at high heating rates, you see the activation energies are considerably lower. So at high heating rates, you're really not probing bond-breaking reactions quite as much as probably you are looking at mass transfer limits in the rate at which processes or oxygen is being liberated. And we need to think about how that oxygen transport is really occurring inside an oxidizer. So this is now the release temperature of oxygen that we measure with our mass spectrometer. And then we mix this with aluminum and measure the ignition temperature. Now, if there was a correspondence for when oxygen comes out and when the system ignites, everything should follow a dotted along the diagonal. But clearly, it does not. You know, some of them follow the line. Okay, there's a correspondence between when oxygen comes out in the gas phase and when it ignites. But then there are examples where, you know, the system ignites before oxygen ever comes out. The oxygen release occurs late. And there are examples where, you know, oxygen release occurs early and the system ignites late. So there's no real way of saying, oh, there is this correspondence between when oxygen comes out and when the system ignites. So we have to think about it in some other way. Certainly, this suggests that there's condensed phase processes going on. If the system is igniting at this temperature for bismuth oxide, but it has never released oxygen, it must mean that it's going on in the condensed phase. So we have to think about how do we think about that occurring. So it's very hard to look at all these different kinds of materials and do comparisons. They have different crystal structures and different particle sizes. There's just no way of doing a systematic study. So for our purposes, the way we did a systematic study is we made a well-characterized oxidizer. And in particular, we made a class of materials called perovskites. They're very well known in the fuel cell community and ion exchange processes. But they're not used as oxidizers in the way that I'm going to use them. But for our purposes, because they have this very regular structure, and they have this AbO3 chemistry, where A is a lanthanide, which is the A site, which is a large, low valent metal. And the B site is usually a small transition element. And then the red ones are oxygen. The advantage is that you can mix and match any kind, well, not any kind, but a variety of different compositions and still keep the same crystal structure, which is important for us. So I'm going to give you that, approach this from the point of view of changing the redox properties. So we're going to make a large range of perovskite systems by aerosol growth. The details are not important, but they're all lanthanum, strontium based, but then I'm going to dope them with either chromium or cobalt or iron. And the reason for doing this is the following. So I'm going to have 3 different B site atoms. This is the chromium, the cobalt, and the iron. So the 8 site substitution, which is normally lanthanum, I'm going to substitute with strontium. On lanthanum is a +3. If I put strontium as +2, that means I've put less positive charge. And by charge balance, that must mean I'm going to have to put less oxygen in. So by putting strontium instead of lanthanum, I'm going to force the system to have less oxygen by charge balance. So now I can put vacancies into the structure in a very controlled way. And we're going to see what that does. So first I got to see, how does the oxygen release compare to ignition temperature? And everything is above the diagonal. Now, what does that mean? It means that these systems must be igniting by condensed phase ignition, because it ignited before oxygen came out into the gas phase. So this is a condensed phase process that we're going to look at. So ignition of systems rely on heterogeneous condensed state reaction. And therefore, that must be an oxygen ion transport. So now we can make all these particles of all the same size, all the same crystal structure, and then we can see how they behave. So the oxygen ion conductivity, or movement of oxygen ions, is proportional to the vacancies, the places where it can hop to, and the mobility, how fast an oxygen ion can move. So those are 2 parameters that are important. And that we can vary by this delta parameter by putting strontium in as to induce vacancies. And this is an intrinsic property. But we think that this should be proportional to the bond energy. The ability to move oxygen should, I've got to break an oxygen metal bond, I should expect it to be proportional. Now we can estimate the average bond energy. There are people who have figured out rough measurements, rough calculations using bond enthalpies of reactions for binary systems to estimate average bond energies in complex systems. We're going to use that. So I'm going to take all our data and I'm going to put it versus the ignition temperature. So this is our experiment on the x-axis. This is our measured ignition temperature. This is the calculated bond energy. And amazingly enough, you can see it follows a trend quite nicely. That is that ignition and bond energy are related. We would expect that to be the case, but this is the first demonstration that I'm aware of that ever demonstrates anything remotely like this. So there's this very nice demonstration of the within classes of reactions by changing both the B site and the vacancies that one can get these correlations. So that's the first piece to understand how we can design oxidizers. Another approach is to think about electronegativity. So electronegativity is proportional to the metal-oxygen bond covalency. How covalent a bond is or how ionic a bond is depends on this electronegativity parameter. So a high electronegativity difference means the metal-oxygen bond is more ionic. And if it's more ionic, the perovskite should be more stable. So if it's more stable, one would expect a higher ignition temperature. And we can compute the electronegativity in a perovskite. Again, that's been worked out by others, how to do that, how to calculate composites. And now I plot that. And again, we see a very strong correspondence between the ignition temperature and the electronegativity. In other words, the more ionic I make the oxide, the higher the ignition temperature. So the ionic character of this structure can be used to tune in the ignition behavior of systems. So again, we can relate to a fundamental parameter, a microscopic parameter of the material. Now, is this generic? So here is, I've shown you everything for aluminum, but now I'm going to do boron and carbon and tantalum. So I'm going to now make it for a whole range of fuels. And so here is ignition temperature versus average bond energy. And this is all the data for perovskites. And so for each family, the black ones are the aluminum, red is boron, blue is carbon. You can see that they follow the same trend. And we can do the same thing with another class of materials. We did doped bismuth oxide, which we doped with other materials again to change their average bond energy. And so they show a different trend, different slope. They're lined up differently, but within a family, you see they do follow the same trend. And I can take all this data and look at the role of oxygen vacancy. And you can see that as I increase the vacancies inside the crystal, places for oxygen to hop to, where there's an opening, there is a correlation that the more vacancies I put in, the easier it is to get the oxygen out, and the lower the ignition temperature is going to be. And then the trend we start to see with electronegativity. Here are the perovskites with their electronegativity. The doped bismuth oxide have lower electronegativity differences, and their ignition temperature is lower. So, we have these family of curves that summarize that this behavior of the oxidizer is independent of fuel and correlates with the behavior microscopically of how oxygen can be tuned to move. So vacancy concentration, the higher the vacancy, the lower the ignition temperature. The bond energy, the higher the metal oxygen bond energy, the higher the ignition temperature. And the higher the electronegativity difference between the metal and the oxygen, the lower the ignition temperature. So one concept that's been central to almost everything that's been done to drive the idea of using nanoscale materials is that high surface area to volume ratio lead to faster reactions in combustion. But the reality is it doesn't seem to work quite as well as we'd like. So this is a conceptual plot. Actually, it was first really, the plot was first made by Rich Yetter, and I'm adapting it for a different purpose. But this is burn time versus particle size, and there's lots and lots of data, and this plot just sort of conceptualizes what you see, that there's a high sensitivity for particle size when the particles are large. You get the d squared burning law that some of you know from droplet burning. And then when particle sizes get smaller, there's a surface burning, and so you get a scaling with diameter. And then when you get to the nanoscale, things don't really look so good because the scaling with diameter falls dramatically. In other words, there isn't as much advantage to going to smaller particles if you have such a weak dependence on diameter. Now, why would you get this? Theory doesn't explain this. And if you look at what actual nanomaterials look like, this is what they look like. And so what is this particle size? Is it the size of this aggregate, or is it the size of the little object that comprises the aggregate? In other words, the primary particle size. So what is the relevant particle size? And really the reason I ask this is because this aggregate can turn into this object on the right. And if it does, then its effective surface area is much, much lower. And so you would expect it to react a lot less. So if you look at two aluminum particles, this is a molecular dynamics simulation with its oxide shell around there, and just heat them up, you start to see them coalescing together. And they coalesce at a temperature much lower than what you would expect. Now, why is that when you have this oxide layer around there? The reason is the moment oxygen diffuses into that, aluminum diffuses into the oxide layer, it's not aluminum oxide anymore. It's something a lot softer. And so we would expect that these particles are not really as small as we think during the combustion process. And so what you would expect is these particles to just mush together, if you like. And we've spent a lot of time thinking about this problem. And I'm going to just summarize some results. I won't show you the experimental results demonstrating this, but I'm going to show you some scaling laws. What we've done here is we have shown that the time to coalesce divided by the primary particle size, this is this little object here relative to the whole object, as a function of the number of particles in an aggregate. So this has 1, 2, 3, 4, 5, 6, 7, 8 particles in this aggregate. So as a function of number of particles in this aggregate, really scales with the fractal dimension of the object. So this is molecular dynamics simulations. And these black lines are fits, and we can fit to one expression now. We can get the sintering time is proportional to the number of particles in the aggregate, effectively to the fractal dimension power. And then there's viscosity and surface tension in here and the particle diameter. This allows us to estimate sintering times. So if I were to go ahead and use this scaling law on typical particles, what I would get is time scales on the order of less than 15 microseconds or so. Characteristic reaction times in reaction cells are on the order of 10 microseconds. That's the pressurization rate we know. In other words, the fusion time is shorter than the combustion time by a lot. In other words, by the time we are actually doing combustion, the particle size that we thought was here may be here. And so this curve is wrong because this particle size scale is wrong. Now, why does this matter beyond, oh yeah, it's kind of cute that this scaling law is different, is that if we've gone to the trouble of making a nanomaterial, and then we lose the nanostructure before we ever get the energy out, we sort of wasted a lot of money in making these nanomaterials, if you like, because there are issues and problems with using nanomaterials. So we've spent some time thinking about how to deal with this. One of the strategies to overcome this loss is to use materials that have gas generators. So if I make a composite of nanoparticles and I were to put a low temperature gas generator, maybe I could puff it out like an airbag, and maybe that would help things. And so we have a process to make these gelled microparticles. Essentially, they're large particles that are comprised of nanoparticles. So here's the microparticle, and if I zoom in, they're nanoparticles, but inside there's also a gas generator that acts both as a binder and as a gas generator to puff things out. And this works quite well, actually. Here is the pressurization rate of these materials in their nascent form, and these materials as one of these mesoparticles. And you can see that the mesoparticle-based materials, as a function of binder content, which is the gas generator, significantly outperforms the same chemistry. So the chemistry is the same, it's just the architecture is different. So it's just an example of using architecture to perhaps get around the idea of this sintering. And we've looked at the particle sizes that come out, and they are in fact much smaller. So I won't show you those details, but effectively, this approach minimizes the sintering. And you can see the combustion dynamics are very, very different. Here is a flame with nano aluminum with an average burn time of 4,000 microseconds. And these microparticles are a factor of 10 faster. The flame is much more compact, it's much more dense, it behaves completely differently. And this is just architecture. Chemistry is really the same in all these systems. And we've spent a lot of time looking at other systems that behave similarly in order to get this, to do this. And the last topic I'm going to talk about is direct imaging of the reaction front in 3D printed composites. How do you package these particles together? So here is printed material, and you can see the burning. But what we'd like to do is look microscopically. And so what we have is we print it now onto a glass slide, and we do microscopy on this. And what we'll get is images of the reaction front. Since this is the color camera, we can convert this into pyrometry to get the temperature. And you can see we can get a gradient within a particle to get things like heat fluxes. And then we can take that microscope slide and look under an electron microscope and find that same particle. This particle is this particle, and look at what those materials are made of. So it's a powerful technique. I'll just summarize some example results. So here's what I showed you before. And now this is what it looks like under a microscopic case. It's a little bit slower. Try and speed it up a little bit. Here we go. And you can see now the reaction front is hopping and leaving behind large particles. Remember, we're starting with nanoparticles, but we're leaving behind large particles. Those are the sintered particles that were occurring on this system. So we can track what's going on, and we can do post-inspection of these materials after the fact to see what we left behind. So this is what we left behind, and then we can actually find exactly that material, exactly those positions. So this particle here is that particle there under an electron microscope, and then we can do post-interrogation to get things like compositional mapping, et cetera. So from this kind of information, we can get things like the thickness of the reaction front. What is the effective reaction volume? In other words, that creates the sintered particle size, because we know what this is from the post-inspection. So we can work backwards and get what is the effective volume of particles that's sintered and what their time scale in sintering is in this system. I won't go through those details, but we can also get the reaction front corrugation and the local velocity in the reaction front. So we can get the local microscopic velocities and compare that when we integrate all the velocities to the global average velocity that you as an observer see. This length scale is 500 microns. So it's a small length scale we're looking at. So we can estimate then how big is the flame area relative to the geometric flame area. And this we call the flame corrugation. In other words, in this example, the corrugation factor was 1.4. The flame was stretched out 1.4 times, similar to a turbulent flame where the flame area is stretched out. And that is what gives you the turbulent flame speed enhancement over laminar flame speed. And we can also get the PDF of the velocity distribution from these little microscopic regions. So you can see there are particles there are regions with very high velocities and low velocities, and this red line is the average. And the average of this curve corresponds reasonably well to the global average we see macroscopically. Now, to do more controlled studies, we worked with a group in France, Dr. Carol Rossi, and she can make thermite systems which are very well regulated laminar structures of fuel and oxidizer. This is aluminum copper oxide. And so we can look at the burn behavior at the macroscopic level, and then we can look at the burn behavior at the microscopic level in the way I told you. What we're interested in knowing is the global burn rate really just the microscopic burn rate times the stretching of the flame? Is the stretching of the flame really what's responsible for an enhanced global burn rate? Because if it is, it means you should do more of that. You should figure out ways of corrugating the flame front in order to enhance the burn rate and the energy delivery rate for the same chemistry. And so the microscopic view is shown here. These are two different times. This is what a temperature profile looks like as a function of distance in these microscopic systems. And again, we can get the corrugation of the flame front and get the velocity distribution PDF. So this is the velocity distribution, and this is the flame front corrugation. And we can ask, does that equation up here really work? And it sort of does. This is what the equation would tell us based on these two pieces of data. And this is what the measured global burn rate is. So roughly speaking, they're actually quite well. And this suggests at least that we should be thinking about the idea of architecturing materials to force corrugation in the flame front as a way of enhancing the global burn rate for the same chemical systems. And we can, this was of course for these very nice laminated structures. We've also looked at more practical systems by directly looking at the interface reaction in nanoparticle laminates. So the same idea, but now we're going to look at laminated structures of fuel and oxidizer, but made of particles. We're going to make layered particle structures, and we're going to interrogate this interface. So these are the layered structures that we've made. The colors denote whether it's a fuel or an oxidizer. These are aluminum copper oxide, but remember they're particles now. They're layered particle layers. And so this is what these interfaces look like as a function of the spacing between the layers. So when the layers are very closely spaced, the reaction front looks sort of homogeneous. But when they are separated with higher spacing, you see this fingering structure. And that's going to be related to the mass transfer limits associated with moving oxygen from one place to another. If we look in the after inspection, the layers are still there. In other words, the layers have not been destroyed. The layers still exist. So the thing that's moving really is some gas phase species, which of course has to be oxygen. And we've modeled this, and I don't want to get into the model, but again, to show this fingering behavior, the model does in fact show more or less a fingering type behavior between the copper oxide layer and the aluminum layer thermally. And that's because this copper oxide layer is endothermic because it's losing oxygen. The exothermicity is occurring in the oxidation in the aluminum layer. And this is burn rate versus layer thickness. So the more thicker the layers, the lower the burn rate should be, obviously, since they are have a higher mass transfer distance to move. So we can now ask things like sensitivity analysis. How sensitive is it to the thermal diffusivity, for example? That's an important parameter when you think that velocity, if you think about premixed flame theory, velocity should be proportional to the square root of thermal diffusivity. We can compute the sensitivity coefficient from this model the log of the velocity versus the thermal diffusivity should be 0.5 by theory. And what do we see experimentally here is this is what laminar flame theory should be, and this is what we see. So when layers are under 50 microns, they act like a premixed layer. And when they are larger than that, now we're sort of mass and heat transfer limited, and there's more sensitivity in the sensitivity parameter. We can compute other things. This is a Dom-Kohler number, which is, and there are many ways of defining a Dom-Kohler number. This Dom-Kohler number is the reaction rate of aluminum divided by the mass transfer rate of oxygen. And if I take that and I plot that, the log of the burn rate versus this Dom-Kohler number, and we plotted it this way because the derivative of this is a sensitivity coefficient. You can see that when we're in this green region where things are very sensitive, this is the region where you want, this is the diffusion limited region, but it's the region which is most sensitive. So this is the region where you can manipulate the process. There's not much you can do up here other than change chemistry. But over here, you can change architecture and you can change the nature in which you put things together for the corrugation or for whatever it is. And this is where the system will be most sensitive to the architecture that you present in the system, and therefore the ability to control burn rate, both in direction and magnitude. So we took all the data, which is to say the laminates that are sputtered. So though these are very, very small bilayer thicknesses. So those are the data up here. And then the particle layers are the ones down here. So they have much larger length separations. And you can see that you can put the burn rate versus bilayer thickness all on one curve. And the energy release rate also on one curve. So what we're doing here is we have 3 orders of magnitude in length scale, leading to 5 orders of magnitude change in burn and energy release rate. So what I'm hoping to get one to appreciate is the fact that by tuning the architecture, we can use it to learn something about the reaction kinetics and the reaction dynamics, but hopefully, more importantly, we can use it to engineer architectures that don't have to be homogeneous everywhere. You could have different architectures at different length scales at different places by different printing methods in order to tune the behavior that one is interested in energy release systems. So with that, I'm going to stop and say that, I hope I've shown you that these high temperature processes typically are quite fast and require specialized tools. These metal-metal oxide reactions are actually typically driven by condensed phase reactions, even under extreme heating conditions. And that if you knew enough about the relationship between atomic structure and microscopic behavior, that you could use that to tune thresholds and energy release rates. And that loss of nanostructure is actually faster than combustion. And this requires special thought if we're going to use nanomaterials to their maximal benefit. They're expensive, they're difficult to implement, they don't process well. And so if you're not using them intelligently, you're sort of wasting money, if you like. And with that, I'm happy to answer questions, and I appreciate your taking the time to listen.